So thank you very much, Zhaomin Wang, for agreeing to give this month's Steering Committee Science talk on impacts of high-frequency winds on the Southern Ocean circulation and Antarctic sea ice. And Zhaomin used to work as a colleague at the British Antarctic Survey, and we still see him around a lot. And works at Hohei University in China, and obviously is presenting with a range of colleagues here. So, Zhaomin, would you like to begin?
Okay, thank you, Tom. Thank you, everybody, for coming to my talk. So today I'm going to talk about this title Tom already mentioned. This is a collaborative work with several people like Zhaomin Wang from the University of East Anglia, Yang Wu and Xiaolin from my university, and David Monday from British Antarctic Survey. Okay, so the brief outline is here. I give a short introduction and describe the model and talk about the results. I also like to talk about the high frequency winds in coupled models and the trends in high frequency winds in reanalyzed data, and then give a short summary. So we know the wind stress is a nonlinear function of surface winds. If we want to calculate the mean wind stress over a certain time period, we have to include the mean wind plus the wind perturbation. By removing this component contributed from the mean wind, we can get the mean wind stress contributed from high frequency wind by this formula 4. So this part from the high frequency winds is not small. So a long time ago, a lot of study has already realized these high frequency winds contribute considerably to mean wind stress. It could be as large as 20% in the middle and the high latitudes. And of course, this high frequency wind can enhance the wind power input into the ocean. And using the mean wind, we can also underestimate the heat flux. Like, for example, by 90 watts per meters over the western boundary region, and by 40 watts per meter per square meter in the tropics. So given the high frequency wind is so important in the wind stress calculation and also in the heat flux calculation, there are already a lot of modeling study. But for the ocean circulation, they mainly focus on the North Atlantic. And for the sea ice, they look at the Arctic sea ice response to high frequency wind forcing. And in the sea ice investigation for the high frequency wind issue, they used slab ocean model or mixed layer ocean model. Here we look at the impacts of high frequency wind on the South Ocean circulation and Arctic sea ice using a high resolution global ocean sea ice model. This model is called MIT GCM Echo 2. I'm not sure if everybody knows this here. It's a global ocean sea ice model with a cubosphere configuration, illustrated by this one with 6 faces. The horizontal resolution is quite high. It's 18 kilometers. It's 80 per meter in the South Ocean with 50 vertical levels. It's uneven levels ranging from 10 meters near the surface to 400 meters near the bottom. we use GRA 25 to force the model. Now I talk about the design of the experiments, because this is mainly a modeling work. So in this study, we define the first experiment is called control experiments. In this experiment, we include all the high frequency fluctuations larger than 6 hours, at the time scale larger than 6 hours. For this, the next sensitivity experiments, you can see this frequency is excluded. That means 6 hours to 2 days fluctuation is not included in the experiments, but all other high frequency fluctuation are included. The next one, 2 day to 8 day, that means we exclude 2 to 8 days fluctuations. And the next one is 8 day to 1 month. We remove the fluctuation at this time scale on 8 day to 1 month. We also design another 2 experiments. This one, the first one is a experiment called experiment month. In these experiments, we exclude 6 hours to 2 days, 2 to 8 days, 8 day to 1 month. So we just keep the fluctuation at the time scale larger than 1 month. For the last one, we just want to test if the wind play a dominant role. So we just play with the wind, U and V. Okay, so this is a description of the experiments.
Zhaomin,
yeah.
Sorry for interruption. I need one clarification that when we talk about the frequency, then we also talk about the amplitude. So amplitude of these things, I feel it's a strength. So strength is not coming into the picture. Means I mean, to my mind, that strength is more important than the frequency of the wind, or because I'm not a meteorologist, so I'm not comfortable with this. So strength means amplitude is not coming into the picture here in your this thing. So
you mean the temperature?
No, strength of the wind. So when you are talking about the frequency, but you are not taking care of, or maybe in the coming slides, are you going to talk about the strength of the amplitude of the?
That's true. So we use a filter. So we move, for example, I give a very simple example. If we do the monthly mean, we also remove the stress, at that specific bands, frequency bands. So both the fluctuation and the stress amplitude are removed.
Okay.
Yeah. Okay, so the next one is the results, the model results. So this one is from the control. We see the westerly winds. Now this is wind stress caused by the westerly winds. And the second one is the results. I said it's a 6 hour to 2 day contribution. This contribution is the difference between the control run and the experiments without fluctuation at a specific time scale. I'm not sure if this is clear to you. In the original experiments, we remove the fluctuation at at a specific time scale. Then if we use the control run minus these experiments, we can get the contribution from that, from the forcing at that specific time scale. Now, I just want to highlight this one. 2 day to 8 days fluctuations contribution is the largest one. That means the synoptic forcing is the largest one in the in the contribution to the wind stress. And for these two figures, we see that wind play a dominant role. Now it's straightforward here. So it makes no sense, maybe you think, to compare these two experiments by for the wind stress, because wind, of course, play a dominant role. But we have to remember, in the heat flux calculation, if we suppress the high frequency fluctuation in the temperature or some thermal variables, that can change the heat flux. The heat flux can also change the ocean circulation. But of course, here for the wind stress, the effect is very small. This is a wind stress. The second one, like the wind power input. This is also very straightforward to understand for the synoptic forcing, the wind power forcing. The input, the difference we can see the largest contribution is from the 2 to 8 days fluctuation. So for the surface eddy kinetic energy, now why I want to show this, because if we include the high frequency fluctuation, that can greatly enhance the surface eddy kinetic energy. Also, we see the contribution for the fluctuation at this time scale, 2 to 8 days, is also dominant. This for the eddy kinetic energy. So far, it's a very straightforward to understand these effects by the high frequency wind forcing. So the next one is the subpolar circulation. We know, wind is definitely very important, but the thermal forcing, like buoyancy forcing, can also be very important. So now here, for the 6 hour to 2 day contribution, we see this is the difference between the control run and the run without 6 hour to 2 day contribution. Now we see from the barotropic stream function, we see the Wheeler gyre, Ross gyre, and also even for the Antarctic Australia gyre located here, also enhanced and strengthened. Particularly for the 2 to 8 days contribution, we see the largest strengthening in the Wheeler Sea and also in the Ross Sea. Some strengthening in the Australia Antarctic basin. Also, the wind effect from these two experiments, we see the wind effect is also dominant. Now, the next one is quite interesting. We can see the high frequency wind can have a very strong impact on Antarctic sea ice. So now let's first look at the Tutu area. This black line is from the control run. And this is the second one. The red line is from the experiments 2 days to 8 days. So in this one, we have to remember 2 days to 8 days fluctuation are suppressed. So we see smaller total area. And again, for the experiment 6 hours to 2 days, we see a larger reduction in the sea ice total area. So I remember this is from January to November. We can see the seasonal cycle at each month. We see the reduction in the sea ice total area. Similarly, for the total sea ice extent, we get the very similar results. Now we have to try to understand this. Before I explain the reason for this one, we look at the net heat flux. This is the averaged net heat flux of the sea ice covered region. For the control one, the black one, we see very large heat loss in the sea ice covered region. When we suppress the high frequency fluctuation, we see reduced sea ice loss, heat loss from the ocean to the atmosphere. For these two experiments with the high frequency, the fluctuation shorter than 1 month, all removed, we see the largest reduction in the heat loss. So that means much less heat loss for this case. So the reason is, we think, is for the control run, this is a wind stress imposed on the sea ice. It's called air ice stress. For the control one, we see very large. This is also the average the wind stress over sea ice covered region, over sea ice actually. We see very large air ice stress in the control run. And then we see reduced stress for the other experiments. So if we have a very strong air ice stress, that can enhance the sea ice drift and make more leads or low sea ice concentration region, and also maybe polynya. So that can enhance the sea ice loss and also increase the sea ice extent or area. So that's the impact on sea ice. Now we look at the high frequency winds in coupled models. So we analyzed a lot of models from Sim5. This model provided 6 hourly data, so that's why we can look at the high frequency windy results in these models. It's quite interesting. So because we are interested in wind stress, this is a regional mean wind stress over the South Ocean between 35 degrees south to 65 degrees south. We see very large intermodal spreads from January to December. So we can also see semi-annual variability. This is from the mean wind. Now it's described by mean kinetic energy averaged over the same region. We see the same annual variability in the mean winds. For the eddy kinetic energy, we cannot see the same annual variability. We can only see the largest eddy kinetic energy in winter and small eddy kinetic energy in summer. Both the mean kinetic wind and the high frequency wind contributed to the large spreads here in the wind stress. So it's very interesting to see for these two particular models, we see very different wind stress in August, September, or October. This is caused by the very large eddy kinetic energy here. So for these two particular models, we can clearly see the very important role of high frequency winds in the mean wind stress. So this means there are large spreads, intermodal spreads at the surface winds, wind stress in the mean winds, in the wind fluctuations. So what's going on for the high frequency winds? We look at the results from 2 reference datasets, like INSEP, actually 3, INSEP R1, INSEP R2, and the ERA interim. All these reference datasets show the increase in eddy kinetic energy, this one, the blue one, the increase is very clear. But in the ERA interim, we see a smaller trends than in INSEP R1 and R2. So eddy kinetic energy is increasing. That means atmospheric circulation of the South Ocean is more stormy. A lot of storms, much more storms than before. But the trends are different in different Uranus data sets. This is an uncertainty. So in the Uranus data set, so I give a short summary. So high frequency winds are important in air, sea, and air ice exchanges, momentum, and also heat flux. We didn't show the heat flux here because it's not dominant, but we do see the impact on the heat flux. And high frequency wind have strong impact on the circulation of ocean and sea ice. Not only in the South Ocean, as I mentioned before, in the North Atlantic also, it's very important. This is demonstrated by this modeling study and many other modeling study. And high frequency wind have large uncertainty in coupled climate models. And high frequency winds are getting stronger. The fluctuation become larger and larger, and the high frequency wind need to be better simulated. Okay, so thank you very much. That's all my talk. So I listed some the reference related to this talk here.
Thank you very much. That was really interesting. I have some questions, but first I will see if anyone else has any questions. Great.
Yeah, sure. Yeah, great talk. Thanks very much, Zhaomin Wang. I guess, you know, you had a focus on fluctuations and how they affected surface processes for the ocean. Any sort of thoughts or ideas around possible impact on CDW getting up onto the continental shelf around Antarctica, that sort of at depth kind of process?
Yeah, it's a very good question. So it definitely, you know, because we see the mean wind stress can be changed a lot by the high frequency wind. That can enhance the upwelling of the CDW and maybe also the CDW intrusion onto the continental shelf. We just didn't show that in this talk.
Yeah,
we analyzed the isoprochnous structure, but we didn't focus on the CDW intrusion in our study. We look at the circulation change, but I'm sure there is a big impact on the CDW upwelling. Yeah, thank you very much for this interesting question.
Great, yeah, thanks.
Zhaomin?
Yeah.
Oh, yeah, yeah.
Okay, can I ask a question?
Yes.
Okay, so what's the implication for your study when someone using low resolution GCM?
Yeah.
What's the implication?
For low resolution GCM, we say it's the spectral resolution is low, right? Not for the temporal resolution. So here we highlighted the importance of resolving high frequency winds. We can say for the coupling, for the coupled ancillary ocean model before, they have a different time step for the coupling. Like we can say at the very early stage for ocean only model, we use monthly mean wind to calculate the wind stress. That's very early time. And gradually we realized that's not enough. We have to resolve high frequency winds. So this can be reflected in the coupling. So we need more frequent coupling. Like maybe sometime, people use the coupling to do the coupling just one day. They do the coupling once. Now realize we need to do the coupling 4 times a day. now that's 6-hourly forcing, similar to our study here. Now we maybe need to move hourly forcing, or we need to cover the model together every hour. So even for some other study, maybe they need more frequent coupling, depending on the process, the question they are looking at. So for the spatial resolution, we don't have answer here. Yeah. For the temporal resolution, I think we need to look at the high frequency perturbation.
Can you go back to the previous figures about
Which one?
sea ice and heat flux?
Sea ice. Here.
Sea ice. No, previous.
Yeah.
Before.
Keep going.
Previous. Oh no, the horizontal. Yeah, this one. This is circulation.
Yeah.
Okay, you mentioned that this 2 to 8 day contribution largest.
Yeah.
Why is that? Why is particular that band?
Yeah.
Any reason for that?
Because the contribution of this time bands is the largest to the wind stress. So the wind stress play a dominant role in driving the subpolar circulation, and actually for the global ocean, in many places, the 8 to 8 days, that's synoptic, a cyclone associated with cyclone storm, that makes the largest contribution to the wind stress, to the mean wind stress. So this is the reason for this one to make the dominant role in determining and driving the circulation, I think.
Okay, what's the difference between E and F? The title is the same.
E and F. So for this one, we removed the high frequencies fluctuation at the time scale shorter than 1 month for all the variables. Like even for the humidity and the surface temperature, we do the smoothing. And for the F, we only do the smoothing for the winds. We keep the original fluctuation for temperature and humidity and precipitation also. Yeah. The only difference between these two is the wind. Yeah.
Almost the same, isn't it?
Yeah, almost same. That means the wind play a dominant role. Yeah. In the contribution. Yeah. For the wind stress and for the wind power input, and also for the circulation. Here, you know, the subpolar circulation effect. But still some different, like you can see around Antarctic, for the Antarctic slope current, the thermal effect is not negligible. This is quite interesting. We are looking at this problem right now, not included in this study, this talk. So for the other part, that's similar.
Antarctic slope current, you mean?
Yeah, it's very interesting. For the Antarctic slope
current, isn't that driven by wind somehow?
That means buoyancy forcing. I think it might be associated with sea ice. The sea ice response is very large to different forcing, and in the coastal region we have a coastal plania that can greatly change the buoyancy forcing to drive this Antarctic slope current. So this is an interesting results because I cannot talk too much about this one here.
Okay. Actually, when I did my master's thesis, I analyzed the Antarctic slope, not current, but like a front at the Antarctic slope region with Tom Whitworth and Alex Olsey. 1998, long time ago,
Mhm.
around the Antarctic continental slope.
Yeah.
But anyway,
It's
yeah,
a lot of
very
things
interesting.
are still not clear for the continental shelf region. But
Mhm.
this study highlights the high frequency winds effect on the, the continental shelf region, the circulation. Like Craig just asked if the CDW can have a lot of, change, and if we can see more intrusion. Now we need to look at the Antarctic slope current. So I have to say, we need to do some more work to have a
As
more.
Craig asked,
Yeah.
if you look at some of this vertical section along the
Right. Yeah.
different sectors, that will be very nice to
Yeah.
check whether
Definitely.
CDW, comes
Yeah.
to the continental shelf or just continental slope, whatever. You can check from the vertical section. If your model is good at reproducing CDW, but I believe MIT GCM is very nice.
Yeah, pretty good model. Yeah.
Reproducing this Southern Ocean feature, as far as I know.
Right. Right. Yeah. So particularly for the subpolar ocean circulation, we found it's a good model. Yeah.
Right.
Not perfect, but it's better than many other models.
Right. Okay.
Yes, Zhaomin.
Yeah. Sure.
Yeah. So actually, the figure A, it is typically of a. This is a typically pattern of the westerly. Is actually in one of my recent paper. I have in an Indian sector the increased sea ice. Actually, I explained in terms of the role of the westerlies. So basically, it's bringing sea ice from the Weddell Sea and then stacking over the in the Indian sector. So, but I did not look at that micro scale, that the frequency, high frequency wind. I overall invoke that this is because of the wind stress that is bringing sea ice and stacking over the Indian sector, or maybe increase in the in situ sea ice formation. Both could play. So this could be a good, actually in my work, it will be a good at a micro scale.
Right.
Now, yes. Now coming to my question, that in the total intra-annual variability, how much percentage that can be explained by this high frequency wind? Means in terms of some number. Let's say you have a temperature, maybe other many variables, many factors. But did you have some quantification, some estimate that okay, the intra-annual variability, this much percentage of the intra-annual variability can be explained by this high frequency winds? And if you can do that, then in a temporal scale, means let's say if you have after 79, with time, maybe regional or different oceanic sector, that quantification would be really helpful to explain many of the regional oceanic sector sea ice variability.
Right. That's a great question. So I have to say we didn't look at the sea ice drift from the Weddell Sea to the Indian Ocean, Indian sector. We didn't look at that detail. I'm sure, after we include more and more high frequency wind, we see much more enhanced sea ice drift. So definitely there is a big change, a big response to that. So it's interesting to look at that. Yeah. So first I have to say, but for the contribution from the different fluctuation to the different variability or change, we didn't quantify these things yet. In this talk, we concentrate on the shorter fluctuations within a month. So we want to particularly highlight the importance of the synoptic forcing in high frequency forcing. That is more important, the synoptic from 8 to 8 days. So it's definitely interesting to quantify this thing in the variability or trends at many different time scales. So I think there are a lot of things to do in the future. So we have to rely on analysis data, and also we can also look at the coupled model results. As I mentioned, in random data, we also can see some uncertainty. In coupled model, a lot of uncertainty. So we have to improve this to reduce this uncertainty first, to give us some confidence on the results.
Yes, another this extending to Kim comment. So the CDW is now in terms of, let's say, contribution of heat to the melting for the West Antarctic ice sheet.
Yeah.
So CDW is actually now we have a consensus that CDW perhaps playing the greater role because melting is from the bottom. So maybe this kind of your micro scale feature like this high frequency wind that perhaps modulating the CDW and then increasing heat flux with time, and that finally contributing to more melting of the West Antarctic ice sheet. So in a vertical section for a West Antarctic ice sheet, those regions, maybe Amundsen Sea or near about where the melting is more, maybe in a vertical profile you can see that how this high frequency wind is actually playing a role, or how they are modulating the CDW.
Right,
incursion.
Yeah, for the Antarctic ice shelf and ice sheet, mass balance. So how will the base melting change? So maybe we need to particularly look at the mean winds in the Bering-Southern Sea and Upton Sea, and also the high frequency winds in that region. Yeah, both. Yeah, it's interesting also. we didn't look at this detail so far.
Yes,
Yeah.
Quite interesting. Thank you very much.
Yeah, so there's plenty to look at, and I was interested in the coastal region because we had this project looking at Antarctic coastal winds just getting going at the moment as well. So looking at the variability and as well as the sort of mean winds is clearly important. But my I guess it's a question or possibly more of a comment, but you showed the biases in the CNET models, with some of them showing quite large biases in the autumn, and I wondered whether that might be associated with the autumn peak in semi-annual oscillation in sea level pressure. We have this, you can sort of see it there, the twice yearly peaks in sort of March and April, and then August, September. Yeah, and as the storm track contracts and intensifies at those times of the year, and the models that sort of outliers, it looks like they are is it MIROC or MRI? I think it's MRI models in the top panel have that extreme peak in the spring, southern hemisphere spring season, August, September. I wondered if that might be, if there's something with the way they represent the storm track in that season that could be having an impact there.
Yeah, so we didn't go to that deep to understand the reason. So it might be worth exploring further this issue to understand what you just said. So it's difficult to fully understand the bias, the intermodal spreads. But for some season or some model, maybe it's possible.
But it's certainly, it looks like in the wind stress and the mean kinetic energy, it looks like quite a clear autumn and winter, autumn and spring
Right.
peak. Anyway, so but that was it really from me. Has anyone got any final questions? If not, thank you very much again, gentlemen. That really was very,
A lot
very
of
interesting.
discussions.
Yeah,
Thank
and really
you.
good to
Thank
hear.
you, Zhaomin. Thank
Thank
you.
you. Thank you.
Thank
And
you.
I will share this recording as per usual. And then next month, I noticed it's myself down to give a talk. So I will have to think of a title and put that down. And I will see you all in a month.
Okay.
If either on
see you next
recording
month.
or yeah. Thank you very much.
Thank you. Bye.
Bye.